Hello. Okay, so this is our second little mini lecture of the course, and we're going to talk a little bit about one-dimensional motion. And to talk about one-dimensional motion of anything, you, me, a baseball, whatever, we're going to need to know about position, displacement, velocity, and acceleration at the very least. Okay, and all of those are bound up in a little subset of physics called kinematics. Okay. And we're going to talk about 1D kinematics, right? And that means that we're going to be considering just motion along a line, right? So consider throwing a ball straight up and having it come straight down, right? The ball is moving up and down, but we don't have to consider any other directions. So yes, this only applies to a certain subset of objects, but it's going to lay the groundwork for everything we do with objects and the motion thereof for the rest of the semester. So this is fundamental stuff. And if you already know it, great, okay? And you will be able to skip around in this video and get the good stuff. But if this is your first physics class, or if it's a little fuzzy for you, hopefully this helps a lot. All right, so first, coordinate systems. There we are, underline again, okay? Now, coordinate systems and setting them up is one of the most important things you can do in physics, because you need to know, well, is positive in terms of a number that you might have for one of these important quantities, position, displacement, velocity, that kind of thing. Is a number that's positive mean you're moving to the right or up or down or north or east or west or however you want to define the direction? We need to have a coordinate system that tells us that. And coordinate systems in 1D motion are lovely and simple, because all you really need is what you've got here. You need a line. I've done left, right. You can do up, down, whatever you think is appropriate. But that's all you need, okay? And at this point, then we can define a few things about that, okay? Now I've defined here with a little black arrow the direction that I'm going to consider positive. And this is a pretty standard one, like if you're moving to the right, positive, kind of like the positive x-axis of a xy plane. And maybe I'll put in a little plus there just to remind us, okay? But in other words, the position of the object going from left to right is increasing. And I've put some more fanciness on here. You don't have to do this with your coordinate systems when you're solving problems unless you really want to, but just so we have some numbers to deal with. And this I've labeled on our axis the origin. So right here is our origin. And right here is 5 meters away from the origin. So this would be 4 and 3 and 2 and 1. Okay? I guess 6 over here. And if we're talking about an object, if we're doing this live, usually I'm just walking back and forth in front of you in the classroom, and that's why I picked this unit, meters. But you can imagine any object, me or something else, a bicycle, a skateboard, moving from the origin, which we can set pretty much anywhere we like, right? We're creating this coordinate system. Nature doesn't care whether we set our origin at the left-hand side of the classroom or the right-hand side of the classroom or this side of the bedroom or that corner of the bedroom or wherever you happen to be. So we're going to say it's right there, and we're going to say whatever object we're considering, well, that object started right there at the origin at 0 meters. And over some period of time, we're not specifying that, we have that object moving to about, well, what does that look like on our coordinate system? About 5.5 meters, okay? So, what does that tell us? Okay, well, obviously it tells us the position at each one of those times. And if we want to know something about the distance, or rather the displacement of that object during that time, okay, we can subtract its final position. Right, so final position I will generally write in this way, x sub f, so f the subscript for final, and the initial position, right, so it's sitting right there at the origin at 0 meters. The difference of those two things, final minus initial, in other words, delta x, the change in position, that is a displacement. We'll talk a little bit about both, well, a little bit now and a little bit in the future about how that's different from distance. And So by definition, okay, displacement only cares about final initial position. So if, for instance, I were to wander all the way across the classroom and then come back to the middle, and that's where I decide my final position is going to be, well then all of that movement all the way over to the right-hand side or to the right-hand side of the classroom, for instance, is not going to matter, right? Only the final and initial positions matter. When you're talking about distance, usually you're adding it up like the odometer of a car as you go along. So if you get in your car and you drive from my home here in El Cerrito, California, to Vallejo, where Cal Maritime is, and then I turn around and come back, well, if I were to just consider the initial position, so here in El Cerrito, okay, El Cerrito, and then I were to get on the highway and I drive and go across this Carquinas. I'm not a good map drawer. And then I get to Cal Maritime. Okay. There. Okay. You get to see some notifications from my calendar. And then I turn around and I come back. Well, my final position and my initial position are the same thing, right? Beginning of the workday, end of the workday under normal circumstances. And so my displacement for that whole day is 0. Whereas if I think about distance covered, so distance, shorthand, would equal, I don't know, whatever this is, about 17 miles one way. So my odometer would probably add about 34 miles, okay, using the common units, all right? So that's the difference between displacement and distance. Okay? If you're all moving in the same direction, well, then, distance and displacement are very similar things. There is one difference, though. Displacement is defined as a vector quantity, meaning that it has both magnitude, sort of its size, and direction. Now, in this example where whatever object this is, say it's me, walking across the classroom, has gone from 0 to 5.5 meters, well, then the direction is to the right, or in our chosen coordinate system, that's a positive 5.5 meters because our final position is greater than our initial position. So that direction and the magnitude of the displacement is inherent to that quantity. If you talk about distance, well, distance does not have a direction associated with it. I mean, you could come up with one. You could say, well, I covered 5.5 meters of distance, and I did it in that direction. But those are two separate pieces of information. And when you're talking about a distance like going from El Cerrito to Cal Maritime and then coming back, well, that 34 miles was covered in all kinds of different directions, right? One going along the highway towards Cal Maritime and one going along the highway away from Cal Maritime. And that makes defining distance or defining a direction for distance very difficult, okay? So what distance is it's sort of the, look at me spelling, is the sort of scalar analog of displacement. So displacement has a magnitude and direction. Distance is a scalar because it has only magnitude. Okay? And we'll run into lots of examples of scalar quantities. Energy, for instance, is a scalar quantity that we'll study in this physics class. Temperature, which we won't study much or very little in this physics class, that's another scalar quantity, an important quantity, no doubt, but does not have a direction associated with it, only has a magnitude. Mass, again, just an amount of something. Mass in particular, it's kind of ridiculous to define a direction for, and that's another example of a scalar quantity. Okay, now to avoid this little mini lecture from being too long, I'm going to cut it off right about there, and when I start the next one, probably later today, and hopefully I'll get up there today, the 25th of August, we'll talk a little bit about velocity and acceleration, which are natural extensions of displacement now that we've sort of got that definition laid out there for us. Okay, so thanks for listening, and I will see you then, so to speak.